Welcome to the ProTips video series designed to arm biology learners with background knowledge needed to succeed during upcoming lessons. I'm Professor Workman, and today's ProTips are about working with data. Data refers to multiple observations. It's a plural word. It is sometimes best described with words. This type of data is called qualitative, like quality. It may describe a category, like whether a person is female or male. Another example of qualitative data is used versus new books. These categories describe the type of book or person, the category of book, something to do with the book's identity that is best described in words rather than numbers. The other type of data does take a numerical form. This is called quantitative, like quantity. Examples of quantitative data include measuring someone's height or counting the number of eggs laid by a hen. These observations are numbers. These quantitative or numerical data can be further subdivided into count and measurement types. Count data comes in whole units that cannot be broken down into parts. An example is the number of eggs a hen laid. She never laid half of an egg. Eggs come in whole, discrete units. Other examples of count data include your red blood cell count or the number of students in my class. I've never had 25½ students. Count data are nice, whole numbers. Contrast that with measurement data, which is continuous. You can logically break down each unit into smaller parts. These are things like height. You may be a certain number of centimeters tall and a half. Time is another example measurement data. A race runner at the photo finish could have completed the race in some number of minutes and milliseconds. Another example of measurement data is volume of water in a recipe. You aren't limited to whole cups. You can break the cups down into a quarter or even an eighth of a cup. So measurement data are continuous and can be broken down into these smaller portions. Whether working with count or measurement quantitative data or the other kind, the descriptive qualitative data, it's normal to organize your data in tables. While recording observations, scientists organize data into these tables. So here are a couple of examples. Table 1 has count data, and you'll notice that it's simply tallied. This keeps track of the number of observations belonging to each category. Table 2 demonstrates measurement data that requires a new row for each observation. This keeps track of the unique items being measured. Here we have weights of different apples. In order to uncover the answer to a question, scientists analyze their data. Note that each data point may be useless on its own. Research questions are usually answered after considering many data points. Count and measurement data are analyzed in different ways. Each type of data is useful, but they answer different types of questions, so consider these examples. First, let's talk about count data. Table 1 presents count data of the number of female and male students in a class. These data are useful if you want to answer questions like what proportion of the class is female, what percent of the class is male, are men or women more likely to enroll in this class? Here are 3 new questions. From count data, you should be able to assess how many observations belong to each category, as well as how many total observations there are. For practice, let's answer these questions. The first asks how many females are in this class. By looking at that first row of my table, I can clearly see that there are 23 female students tallied. How many males are in this class? Well, 17. The table told me. Now we have to calculate how many total students are in the class. So I add up the female students and the male students taken together. There's 40 students in my class total. Next, we can perform some calculations on these count data to also be able to assess the proportion and percent of observations that fall into each category. So, what proportion of this class is female? The word answer is that 23 of the 40 total students in this class are female. But the math answer asks us to take the total number of females, that's 23, and divide it by the total number of students in every category. So that's the grand total. Since there's 23 females in a 40 student class, 23 divided by 40 is 0.575. The proportion of students in this class who are female is 0.575. Next, test your understanding by calculating the proportion of students in this class who are male. "17 out of 40 total students are male. So 17 divided by 40 is 0.425. The proportion of students in this class who are male is 0.425. Notice that if we add up the proportions of students who fall into each of the categories, it adds up to the number 1.0. That's like 100%. You just practiced an important analysis, calculating the proportion of total observations that fall into each category. From proportion, you can also calculate the percent. To do this, simply multiply by 100. Since the proportion of female students is 0.575, that means that 0.575 times 100 is 57.5% of the class. So 57.5% of the class is female students. The rest, 42.5%, are male. Notice again that the proportions add up to 1 in the same way that percents add up to a 100% whole. Next, let's practice analyzing measurement data. Table 2 presents measurement data documenting the weight of several varieties of apple. These data are useful if you want to answer questions like, what is the average size of an apple? Which apple is the biggest or smallest? Which apple is the right size to match my appetite? From measurement data, you should also be able to assess the maximum and minimum observed values. You can also see from the number of rows in the table how many observations were recorded total. Let's practice. How much did the smallest apple weigh? This is the minimum observation. The smallest apple in this list is 393 grams. How much did the biggest apple weigh? The maximum observation is 531 grams. Those are the Honeycrisps. And how many apples were observed? So here we just count up the number of rows because each row represents one apple that was weighed. There were 7 apples weighed in this experiment. By performing some calculations on your measurement data, you should also be able to assess the average value of your observations and the range of variation, also known as spread, in your data. Let's practice. What is the average weight of apples? Here we take all of the observed weights and add them up. We then divide that sum by the total number of apples weighed. So the average weight of apples in our sample here is 441.1 grams. The next question asks, what is the range of variation in apple weight? So we're wanting to know the spread. To calculate spread, we're going to take the maximum observation minus the minimum observation. Apples all weighed some number falling in this range. And so the spread of the data from max to min apple weight is 138 grams. This slide highlights what you just performed. You analyzed the average apple weights by taking the sum of all the observed apple weights and dividing it by the number of individual apples observed. You also calculated the range of variation, also known as the spread in the data, by subtracting from the maximum observed weight the minimum observed weight. Good job! In summary, you've learned about different data types. There is qualitative or descriptive data that describes categories, and there's quantitative data, which comes in numerical form and is analyzable with statistics. Within the quantitative data, there's count and measurement subtypes. You also learned how to calculate proportion, percent, average, and range of variation. Thanks for watching.
If you liked this video, you might consider watching other videos in the series. Here's my contact information, and I always welcome any feedback. mworkman@pima.edu. Good luck in your biology journey.